Bismillahirrahmanirrahim. Assalamu alaikum. Today we will study about Large Hadron Collider LHC. The LHC consists of a 27-kilometer ring of superconducting magnets with a number of accelerating structures to boost the energy of the particle along the way. The accelerator sits in a tunnel 100-meter underground at CERN, the European Organization for Nuclear Research, on the France-Swiss border near Geneva. Inside the accelerator, two high-energy particle beams travel to 99.9999991% the speed of light before they are made to collide. Hadrons are composite particles made up of quarks and gluons. The gluons carry the strong force which enable quarks to stick together and bind them into a single particle. In LHC, the hadrons used are protons. They are made up of 3 quarks and an indefinable number of gluons. The protons are not fired at one another individually. Instead, they are circulated in bunches inside the LHC, each bunch containing 100 billion particles. Two beams of proton travel in opposite direction at maximum energy of 6.8 tera electron volt, corresponding to a head-on collision at 13.6 tera electron volt. The energy from collision gets converted into matter, producing new particles that allow us to explore nature of universe. Einstein's famous equation E is equal to mc square show mass and energy are related and can be changed from one form to another. Since the speed of light c is equal to 2.998 into 10 raised to the power 8 meter per second, and in Einstein equation E is equal to mc square, speed of light is squared. Tiny amount of mass contains huge amount of energy. As the object approaches speed of light, its observed mass becomes infinitely large. As a result, an infinite amount of energy is required to make an object move at speed of light. Hence, it is impossible for any matter to travel faster than light speed. As we increase energy and momentum, they only get a very small fraction closer to the speed of light, never reaching it. However, their energy and momentum increase considerably. Accelerators use electromagnetic fields to accelerate and steer the particles. Radio frequency cavities boost the particle beam, while magnets focus the beam and bend their trajectory. Linear accelerator is exclusively formed of accelerating structures. Since particles do not need to be deflected, but they only benefit from a single acceleration pass. In this case, increasing energy means increasing length of the accelerator. An oscillating electric field is applied across the electrodes connected in series. The charged particle, when traveling through electrodes, is allowed to accelerate if the frequency of the applied electric field is in resonance with the motion of the particle. A linear accelerator comprises a few coaxially organized hollow conductive cylindrical tubes called drift tubes. These tubes are arranged in increasing length in the evacuated tube. The odd tubes are associated with one terminal of radio frequency oscillator, while even tubes are associated with the other terminal of radio frequency oscillator. A source gives positive particles to be accelerated or speed up. The positive particles generated at source are made to enter the arrangement of electrodes. The particles are then accelerated towards C1, and after entering this electrode, they move with constant speed as there is no electric field present inside it. Now, assuming the length of electrode C1 is such that particles emerge out of it exactly when the phase of the alternating voltage is reversed, The particles will be accelerated towards C2. Then the particle enter the electrode C2 and now travel at steady speed, which is more than the speed of the particle at C1. The length of each electrode is adjusted in such a manner that the time taken by the particle inside the electrode is equivalent to half the time period of the oscillator, and obviously the length of progressive electrodes increase. Accordingly, particles acquire extra energy in each gap. In this manner, linear accelerator works. The CERN Hadron Linex are linear accelerator that accelerate the beams of hadron from standstill to be used by large circular accelerators at the facility. LINEC 3, also known as lead LINEC, provides lead ions for LSC and for fixed target experiment. Linear Accelerator 4 or LINEC 4 is designed to boost negative hydrogen ions to high energies. It became a source of proton beam for LHC in 2020. In circular accelerator, the particle repeats the same circuit for as long as necessary, getting an energy boost at each turn. In theory, the energy can be increased over and over again. However, the more the energy the particles have, the more powerful magnetic fields have to be to keep them in circular orbit. There are two types of circular accelerator, cyclotron and synchrotron. Protons leaving the center are attracted to the negative electrode. The magnetic field bends the proton into a semicircle. While the proton is traveling in the semicircular path, the polarity of electrodes reverses. When the proton reaches the gap, the electric field accelerates particles forward because it is oppositely charged. As proton completes each semicircle and are accelerated along the gap, they gain more and more kinetic energy. The radius of the proton's path increases in proportion to r is equal to mv over bq since it travels faster, where r is the radius, m is the mass, v is the velocity, b is magnetic field, and q is the charge. Since the radius of the path increases, and so by traveling faster, it takes same time to travel each semicircle, hence alternating voltage can stay at the same frequency. At very high energies, the particles travel at the speed of light, and their motion is now described by relativistic equations, and their travel time is not the same in each semicircle. To overcome this, careful synchronization is needed to make the electrodes change their polarity as the particles pass through each acceleration section. The magnetic field is increased to keep the particles moving in a circle of constant radius. A synchrotron is a cyclotron wherein the strength of the magnetic field increases with the energy of the particles to maintain their orbital radius constant. The proton synchrotron booster is the first and smallest circular proton accelerator. It contains four superimposed rings with radius of 25 meters, which receive energy of 160 MeV from linear accelerator 4 or LINEC 4 and accelerate them to 2 GeV ready to be injected into proton synchrotron. The proton synchrotron is CERN's first synchrotron beginning its operation in 1959. Today it is a part of CERN's accelerator complex. The proton synchrotron booster, which accelerated the proton to 2 GeV, is followed by proton synchrotron, which pushes the beam to 25 GeV. The protons are then sent to the superproton synchrotron and accelerated to 450 GeV before they are injected into LHC. The superproton synchrotron is the second largest machine in CERN's accelerator complex. Measuring 7 km in circumference, it takes particles from proton synchrotron and accelerates them to provide beam for LHC. The Large Hadron Collider LHC is the world's largest particle accelerator. The collider has 4 crossing points where the accelerated particles collide. 9 detectors, each designed to detect different phenomena, are positioned around crossing points. LHC boosts the particles in a loop of 27 km in circumference to an energy of 6.8 tera-electron-volt, generating collision at the energy of 13.6 tera-electron-volt. The speed of proton in LHC is 99.999991% the speed of light. Therefore, the speed of proton in LHC is equal to 299,792,455 meter per second. We all know speed is equal to distance over time. The circumference of LHC is 27 km. Therefore, the time comes out to be 90 microseconds. A proton beam makes one full revolution along LHC in about 90 microseconds. We all know frequency is equal to 1 over time. The frequency comes out to be 11,100 revolutions per second. A typical fill in LHC lasts 15 hours, which is equal to 54,000 seconds. Total time the particle revolves is 54,000 seconds. Time for one revolution is 90 microseconds. So a proton that survived until the end of the fill must have circled the LHC about 500 million times. Since the momentum is proportional to magnetic field, superconducting dipole magnets with magnetic field strength of about 9 Tesla were developed. In order to increase the magnetic field strength, the LHC magnets operate at 1.9 Kelvin in a cryogenic system with superfluid helium. A large variety of magnets are required to keep particles' trajectory stable. The quality of magnetic field is essential to keep the particles on stable trajectory for about 10 to the power of 8 turns. Small dipole, sextupole, octupole, and dectupole magnets are installed to keep the particles in a stable trajectory. The LHC has 1, 2, 3, 2 dipole magnets which bend the particle's trajectory. It has 474 quadrupole which squeeze the bunches. Magnets of higher multipole order are used to correct small imperfections. In circular accelerator at LHC, heavy particles such as protons have much lower energy loss per turn through synchrotron radiation than light particles such as electrons. Protons are about 2000 times more massive than electrons. Therefore, in circular accelerators, to obtain high energy collisions, it is more effective to accelerate massive particles such as protons. The LHC creates quark-gluon plasma whose temperature exceeds 1.5 trillion Kelvin. The maximum temperature inside the Sun is 15 million Kelvin. The temperature at LHC is 100,000 times hotter than the Sun. LHC at 13.6 tera-electron-volt energy produces temperature comparable to that which occurred very soon after the Big Bang. LHC can reproduce the condition that existed within a billionth of second of Big Bang. After the Big Bang, the universe was thought to be a soup of energy before it rapidly expanded during the period of inflation, which allowed the universe to cool enough for matter to form. The first entities that were thought to emerge were quarks, a fundamental particle, and gluons, which carries the strong force that glues quarks together. As the universe cooled, they formed hadrons, some of which we know as protons and neutrons. In LHC, high-energy protons collide to reproduce fractions of a second after the Big Bang 13.7 billion years ago. The Higgs boson is a fundamental force-carrying particle of the Higgs field, which is responsible for granting other particles mass. This field was proposed in mid-60s by Peter Higgs. Scientists confirmed its existence in 2012 through the ATLAS NCMS experiment at the Large Hadron Collider at CERN in Switzerland. ATLAS is short for a toroidal LHC operator. ATLAS measures masses, channels of production, decay, mean lifetimes, interaction mechanism, coupling constants for electroweak and strong interactions. CMS stands for compact muon solenoid. The CMS tracker records the path taken by charged particles by finding their position at a number of key points. The electromagnetic calorimeter is designed to measure with high accuracies energies of electrons and photons. The Hadron calorimeter is used to measure energy of hadron particles made of quarks and gluons. CMS has large solenoid magnet with 4 Tesla magnetic field that is 100,000 times greater than the Earth. The job of the big magnet is to bend the path of particles emerging from high-energy collisions in LHC. The more momentum the particle has, the less path is curved by the magnetic field, so tracing its path gives a measure of momentum. As the name compact muon solenoid suggests, detecting muon is one of CMS' most important tasks. Muons are charged particles like electrons and positrons, but 200 times more massive. You expect them to be produced in a decay of potential new particles. For instance, one of the clearest signature of Higgs boson is its decay into 4 muons. New particles discovered in CMS will be unstable and rapidly transform into a cascade of lighter, more understood particles. Particles traveling through CMS leave behind a characteristic pattern or signature, allowing them to be identified. The presence or absence of the new particle can be observed. Higgs boson, like many other elementary particles, is unstable and lives for an extremely short time of 1.6 into 10 raised to power minus 22 seconds. The Higgs field is the energy that is thought to exist in every region of the universe. Just like an electron is an excitation of electric field, the Higgs boson is simply a particle which is an excitation of the everywhere permeating Higgs field. The Higgs boson is a fundamental particle associated with Higgs field, a field that gives mass to other fundamental particles such as electrons and quarks. A particle mass determines how much it resists changing its position or speed when it encounters a force. Not all fundamental particles have mass. The photon, which is a particle of light and carries electromagnetic force, has no mass at all. Until now, CERN has mobilized the expertise of scientists and engineers around the world to establish the location of a 91-kilometer ring, 200 meter underground, close to Large Hadron Collider. According to CERN, the construction of future circular collider could start after 2035. After a decade, The first stage will be electron-positron collision. The goal of Future Circular Collider (FCC) is to push energy and intensity frontier of particle collider with the aim of achieving collision energies of 100 tera electron volt. CERN's plan, if executed, would cost tens of billions of dollars. The Standard Model cannot explain following observations: evidence of dark matter, prevalence of matter over antimatter, the neutrino masses. It is these secrets of subatomic world that shape our world. They are the basic building block of our universe. Particle detector, first developed for particle physics, are now ubiquitous in medical imaging. Discovery in physics causes a giant leap in technology. It is on the foundation of physics that other sciences emerge. May Allah bless us all. Thank you for watching. Allah Hafiz.